Today we'll discuss on a quick overview of conversion of regular expression to the DFA. Here we try to work on the conversion by constructing an syntax tree. So we'll have the regular expression 0, 1, the whole closure, uh, 0 or 1 with hash. Why do I add hash? That is the first step where you are supposed to add hash in order to indicate the last position of the string. So when you add hash to the regular expression, you call it as an augmented regular expression. Then the second step is to construct a syntax tree. Here the syntax tree is constructed. Let us try to understand how it works. All the symbols are considered as leaf nodes, and then the operators closure, or, and concatenation are considered as intermediate nodes. So 0 is a leaf node, 1 is a leaf node, then 0, 1, 5 hashes are leaf nodes. Here if you just look at it, 0, 1 uh, is concatenated, that has the highest priority, to which closure is applied. So 0 and 1 is concatenated, to which closure has been applied. And then again you have an parenthesis, it is either 0 or 1. Since you have an parenthesis, that is any sub expression which is considered or represented within the parenthesis is considered as an subtree. So 0 or 1 is considered as an subtree, 0 1 is considered as an subtree, and then it is this 0 1 closure is combined with 0 or 1. So you have a concatenation over here, and then the complete thing is concatenated with hash. That is step number 2. Step number 3 is to position all these symbols. So the positioning of the symbols starts from the left hand side. We will never position the operators or the parentheses. Uh, to your information, parentheses will never be represented in the syntax tree. It is just to force or to indicate the priority of operation. And then your epsilon symbol will not be positioned. The rest leaf nodes will be positioned from left to right with along with the hash symbol, the end marker. So you have 1, 2, 3, 4, and 5. Position is used just to emphasize the characters at that particular position, because you have characters occurring again and again. And then we talk about, we are supposed to calculate four things. The first one is nullable, which is either true or false, which helps you to identify whether the string is capable of generating an empty string or not. Then you have first position and last position. This helps you to identify the set of positions which can occur as the first and the last characters when the string or the substring is generated. And as we have discussed in the class, we have set of rules. So we'll try to consider it one by one. All leaf nodes are capable of generating that string alone, and hence the leaf nodes with the positional value will have false where no empty string is generated. Okay. For the AND operator, it is the nullability of the left child and the nullability of the right child. So for AND operator, you apply concatenation operator, you apply AND. For OR operator, you apply OR symbol. So it is false or false, which is false. For closure, closure always has an ability to construct an empty string, and therefore closure nullability of closure is true. The rest is false. Now the first position. First position of all the leaf nodes are itself. First position of the OR node is the first position of the left child and the first position of the right child put together. Therefore, it is 3, 4. What about first position of the concatenation? You check the nullability of the left child. If the nullability of the left child is false, you take the first position of the left child alone. If the nullability of the left child is true, you take the first position of the left child as well as the first position of the right child. Here, for the concatenation node, the left child is 0, which is at position 1. The nullability of this child is false, and therefore you take it as 1. For closure, whatever comes as the first position of the child takes it here, so it's 1 here. For this concatenation, the left child is closure. The nullability of closure is true. Therefore, I combine the first position of the left child as well as the right child, and it goes on. Then we'll try to calculate the last position. The last position of the leaf nodes or itself. The last position of the R node is the last position of the left child and the last position of the right child put together. So it's 3 comma 4 again. But for nullability, for concatenation, you check the nullability of the right child. If it's false, you take the last position of the right child alone. If it's true, you take the last position of the left and the right child together. Here, for this concatenation, the right child is 1, whose nullability is false. Therefore, the last position is 2. For here, for closure, whatever comes the last position of its child, you take it. So it's 2 here. And then for this concatenation, then the right child is R, whose nullability is false. So I have taken 3 comma 4. For this concatenation, the right child is hash. Again, we have taken the nullability of the right child. Now to evaluate the follow position, you can consider only two nodes. One is concatenation node and the other one is star node. For the concatenation, for the star node, you take its last position, add its first position. So to 2, I have added 1. For concatenation, you take left child's last position, which is left child's last position is 1. To it, I'll add concatenation nodes right child's first position, which is 2. Coming on to, will I consider R node? The answer is no. Coming on to this dot symbol, left child is closure. To left child's last position, which is 3 and 4. We'll add the, okay, so to 2, I'll be adding 1. Here to the left child's last position, 1 second, to the left child's last position 2, we'll be adding the right child's first position, which is 3 and 4. So to 2, I have added 3 and 4. And for this dot operator, that is 3, last left child's last position is 3 and 4. So to 3 and 4, you have added right child's first position, which is 5. So 5 is added. So there ends the follow position. Now we'll try to construct the deterministic transition. Okay. So what is here? This gives you the complete conversion algorithm. First, you construct the augmented regular expression. Then you calculate first position, last position, and a nullable. Now, the first position of the root is the initial state of DFA. You check it and you find the transition. That is what we are going to do it. So the first position, how do I identify the root node? The root node's right child will be hash. First position of the root is 1, 3, and 4. That is your first DFA state. Now, in our class, we have named it as A. So what can we do? This 1, 3, and 4 on 0. In the position among 1, 3, and 4, position 1 has 0 and 3 has 0. So I have taken follow position of 1, union follow position of 3, which is 2 and 5, which is a new state. And then 1, 3, and 4, among 1, 3, and 4, 4 alone has 1. So follow position of 4 is 5. So I have two new states, 2 comma 5. Then this two new states, I have to find the deterministic transition. So you have dtran of 2 comma 5 on 0, 2 comma 5 on 1, 5 on 0, and 5 on 1. If there are any new states, we'll take it up, else we'll finish it. But then if you just look at here, you have supposed to identify the final state. How will I identify the final state? The set which has the last position hash will act as the final state. Here, if you just look at among these three states, 2 comma 5 and 5 has the has the position of hash. Therefore, you have two final states, 2 comma 5 and 5. At the last, we'll draw the DFA for these transition table. So this is how we try to calculate or convert a regular expression to DFA.